Welcome, student pilots. Today, we are tackling one of the most absolutely crucial yet commonly misunderstood topics in all of aviation. As your flight instructor, I don't just want you to memorize this stuff, I need you to understand it in your bones. We're going to bring some really bright, energetic focus today as we completely demystify the aerodynamics of stalls and spins. This explainer is going to give you everything you need to master these maneuvers safely. Are you ready? Let's dive right in. Grab your notebooks and pens right now because you're going to want to take detailed notes on this. Here is our flight plan for today. We're covering introduction to stalls, recognition and recovery, wing design and washout, factors affecting stall speed, understanding the spin, and finally, spin recovery techniques. All right, Section 1, Introduction to Stalls. Let's talk about the pure physics of what a stall actually is. Okay, write this definition down at the very top of your notes. There's a really common misconception among beginner pilots. When they hear the word stall, they automatically think of a car engine dying, like the airplane's engine just quits. Nope. A stall is strictly an aerodynamic loss of lift. It literally has absolutely nothing to do with the engine. It's simply the moment when the lifting force of the wings can no longer support the weight of the airplane. That's the whole shebang. I want you to put a huge star next to this next point. This is the absolute golden rule of flying. We always look at the published VSO stall speed in our manuals, right? Like 48 knots, for instance. But you have to remember, that number is just one very specific scenario, usually power off, wings level at maximum gross weight. The reality is, a stall always happens when the wing exceeds its critical angle of attack, period. It doesn't matter if you're flying at 100 knots or if your nose is pointed straight at the ground. The exact second you exceed that critical angle of attack, a stall occurs. Try to visualize this process in your head. As your angle of attack gets too high, that beautiful, smooth airflow over the top of the wing physically detaches from the surface. And what's really fascinating here is that this separation doesn't start at the front of the wing. It actually starts at the back, the trailing edge, and creeps its way forward. Once that airflow fully separates, your lift just drops off a cliff. Moving on to Section 2, Recognition and Recovery. How exactly does the airplane talk to us before a stall happens, and how do we fix it? As a pilot, you have to train all your senses. When that airflow we just talked about separates from the main wing, it actually hits the horizontal stabilizer in the back. That turbulent air creates a physical vibration you can feel right through the yoke, which we call a buffet. You need to feel that buffet. Constantly cross-check your airspeed and listen for that stall warning horn that's designed to go off 5 to 10 knots before the actual stall. Make sure you write those 3 warning signs down right now. Aerodynamically speaking, here's the magic behind what's happening. As your angle of attack goes up, the center of pressure, which is where all the lifting force is concentrated, slides forward on the wing. At the exact same time, the stagnation point, where the oncoming air splits over and under the wing, slips backwards. It's almost like the air gets sucked into a stall hole, and that's exactly why the airplane loses lift and the nose suddenly feels incredibly heavy. So how do we recover? Well, we basically just run the physics in reverse. Simply push the nose down to instantly reduce your angle of attack. That allows that turbulent, detached air to smooth back out into a nice laminar airflow hugging the wing. Once you regain that smooth airflow, your wings reproduce that solid lift, and your airplane is flying happily again. It's a completely straightforward formula. Let's head into Section 3, Wing Design and Washout. This is where we see how aircraft engineers have our backs. Jot this term down, angle of incidence. Unlike the angle of attack, which you actively control with the yoke, the angle of incidence is literally built into the airplane at the factory. It's the fixed structural angle at which the wing is attached to the fuselage. If you look at an airplane from the side and see the wing tilted slightly upward, that's your angle of incidence. And here is a brilliant piece of safety design called washout. Engineers intentionally design the wing so the angle of incidence is greater at the wing root, near the body, than out at the wingtips. Why? Because as your angle of attack increases, the wing root will hit its critical angle first and stall before the tips do. This is a total game changer, because it means even while the root is stalled, you still have full aileron control out at the wingtips to keep the plane level. Absolutely genius engineering. All right, Section 4, Factors Affecting Stall Speed. What makes your stall speed change from that published number? Take a big note here. Whether you've loaded up the plane with passengers and baggage so it's super heavy, or you're banking hard into a steep turn, your wings have to work way harder to fight off those loads. To generate that extra required lift, you have to pull back and increase your angle of attack. Because you're already operating at a higher angle of attack just to stay level, you are going to hit that critical stall angle a lot sooner, meaning your stall speed shoots way up. Now, visualize the invisible tug of war happening outside the aircraft right now. As your CFI, I need you to always remember this principle. For an airplane to maintain altitude, the upward lifting force from the wings must perfectly equal the downward forces. And those downward forces are your airplane's weight plus the aerodynamic tail down force pushing on the back of the plane. Write down this exact chain reaction. If your center of gravity is too far forward, your nose naturally wants to drop. To fight that, you need more tail down force pushing the back end down. But wait, more downward force overall means your wings now have to generate even more lift to compensate. And how do we get more lift? By increasing the angle of attack. So a forward CG puts you at a higher angle of attack, meaning you'll stall at a much faster airspeed. Ask yourself this really fascinating question. What if the upward lift and the downward weight are perfectly aligned at the exact same spot? Well, you wouldn't need much tail downforce at all, which means way less drag and fantastic fuel efficiency. But there is a massive catch. Without that tail down leverage, your nose becomes incredibly light and sensitive. You end up with an incredibly unstable airplane that just wants to pitch up and down all over the place. Okay, section 5, understanding the spin. This is where we talk about auto roll and auto yaw. Highlight this in your manuals. A spin does not just happen out of nowhere. It exclusively occurs from an aggravated, uncoordinated stall. Both wings have to be stalled, but here's the kicker. One wing is significantly more stalled than the other. When that happens, the airplane completely loses its aerodynamic balance and starts corkscrewing uncontrollably. Look really closely at this terrifying-looking spiral path. The wing that is more stalled is producing way less lift, which causes the airplane to violently roll to that side. We call that auto roll. At the exact same time, that heavily stalled wing is creating a massive amount of drag, pulling the nose in that direction, causing an auto yaw. Those two forces combined are what lock the aircraft into that dizzying vortex. This next fact is completely mind-blowing, so make sure you note it down. When you're sitting in the cockpit during a spin, the world is whirling around you, and it feels like you should be pulling massive G-forces. But aerodynamically, because the wings are completely stalled and basically just falling through the air, the aircraft is only experiencing 1 G. Structurally, the airplane isn't under any major stress at all. Crazy, right? Finally, section 6, spin recovery techniques. Let's talk about the exact inputs you need to break that spin and regain control. Depending on what you're flying, you'll use a specific memory aid for your emergency procedures. If you're in a classic trainer, like a Cessna, you'll use the acronym PAIR. If you're flying something like a Piper Arrow, you might use REAP. When you are actually spinning toward the Earth, you do not have time to whip out a checklist, so you need to have these burned into your subconscious. For a Cessna, absolutely memorize PAIR. P, power to idle, so the engine torque doesn't make the spin worse. A, ailerons neutral. Trying to roll out of it will actually increase drag and tighten the spin. R, rudder opposite to the spin direction, slam that rudder to instantly stop the yawing motion. And E, elevator forward. Briskly push the nose down to break the stall and get air flowing smoothly over the wings again. If you truly grasp the physics we talked about today, you'll be able to handle absolutely anything up there. So I'll leave you with this question to chew on. If you ever find yourself spinning to the left, which foot are you going to stomp on first? Think about it, and I'll see you on our next flight.